Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Lana and her husband Maxim are on their way back from NIPS, where they gave a talk, an oral presentation last week. Lana has done a large amount of computer vision research during her thesis studies at UIUC. She started off doing 3D object reconstruction from contours, then moved over to recognition from texture, and most recently has been doing object recognition from features. So we're looking forward to hearing all about her thesis research.
Okay, thanks. So I will give an overview of the kinds of recognition problems that I have worked on in the course of my thesis research. The first and the sort of most basic problem is recognizing textured surfaces or materials. So we want to develop image descriptions or representations that are invariant to a wide variety of geometric changes. For instance, you can have significant scale changes, non-rigid deformations, perspective distortions, etc. And this is really something that traditional research in texture analysis hasn't dealt with. The next problem, which is vastly more difficult, is object recognition. So we want to deal with things like bikes and motorbikes and people, and potentially we want to deal with thousands of real-world objects. And of course, the kinds of image descriptions we develop have to be invariant to clutter, intra-class variations, hopefully 3D viewpoint change, etc. And another problem, which is related to object recognition, is recognizing a scene as a whole or a context. So we're not necessarily looking to recognize individual objects in this case. For instance, farm buildings, trees, grass, clouds, etc. We want to just recognize the scene as a whole. We want to say this is a farm scene, this is a beach scene, this is a meadow scene, city scene, etc. And these kind of global scene classification tasks can naturally lead into object recognition. For instance, if we know we're looking at a farm scene, we may want to start detecting cows. But we may not want to start detecting toasters, for instance. So this can be a powerful priming tool for figuring out what kinds of objects to detect. Okay, so the kinds of image representations I have designed for in my research were based on so-called local features. So local features are salient image regions. You can see two examples here in the slide. One feature detector is a hairs detector which finds corners. So on this image with windows, it can find corners of the windows, etc. And the other detector is a Laplacian blob detector. So it will find, instead of corners, it will find the actual dark windows and the light spaces between them. And these regions can also be made invariant to various local image transformations. So you can see that these regions look like ellipses. So they're not just points in the image. They have a certain local shape, which we can use either to gain invariance to rotations, local distortions, scale changes, etc. Or we can use the shape as additional discriminative information. So after we detect these image patches, we have to describe their appearance. And the kinds of descriptors I have worked on are basically 2D histograms of image attributes such as intensity values or gradient orientations. So when you have an image patch, you just break it up into several subregions and compute histograms of intensities or of edge orientations in these subregions. Yes?
So for a color image, do you map it to intensity first? And then
Yeah, so I don't actually work with color anywhere explicitly. Everything is grayscale. So this is what I mean by local features, some sort of a feature detection process followed by appearance description. Okay, and next I'll give a brief overview of the image representations that I've developed. The most basic image representation is a bag of features. It has actually not been invented by me, but has been experimented with a lot lately, and is showing to be surprisingly powerful. So once we detect local features, we quantize their descriptors and form a representation which is just a histogram of the appearance or texture labels of the individual regions. So this representation disregards all spatial information. It throws away all information about the arrangement of these regions in the image. It just keeps their appearance. Next, I have recently experimented with a representation which is slightly more powerful because it tries to take these histograms and extend them with some global spatial information. So the most basic thing we can do is just subdivide the image into multiple subregions and compute histograms in the individual subregions. So this retains some information about where things are in the image. And we can do it at multiple resolutions and just concatenate all of these histograms to form some sort of a multi-level representation. And this is particularly suitable for scene recognition tasks, because for scene recognition we care about global facts such as sky is usually on top, etc. But none of these representations are really very good for detecting objects in the image, because they don't distinguish between object features and background clutter. So what we really want to do for object recognition is we want to discard the clutter and figure out where there are some repeatable constellations of these regions. And then when we figure out that there are actually two badgers in the image and their heads have this sort of stable and distinctive appearance, we can have a part-based model. And next I will go over each of these in turn. Okay, so this is a slightly more detailed summary of our bag of features approach for texture recognition. It was introduced in CVPR 03 and was later published as a journal paper. And recently we have done a lot more evaluation in collaboration with postdocs and students of Cordelia Schmid at INRIA. So we start out, as I mentioned, by detecting local features, normalizing them. So if we have an ellipse, we map it onto a circle to eliminate the local geometric deformations and compute appearance descriptors and quantize them and build histograms. Next, sort of a general representation that can feed into a classification or a retrieval task is just computing distances between the different histograms or signatures. And we can either use them inside of a Gaussian SVM kernel, or we can do nearest neighbor classification or retrieval of images, etc. So to really make this framework work well, first of all, we found that we have to combine multiple types of detectors and descriptors. I showed two kinds of detectors, the corner detector and the blob detector. So if we have two detectors, and there are a lot more in the literature, we should run them all and compute feature descriptors for each of them. And if we have several types of descriptors, the final number of sort of feature descriptions of the image we will have is the number of detectors times the number of descriptors. And we can compute a distance matrix for each of them and add up these matrices, and it turns out inside of a discriminative framework, it raises the recognition results. So it really pays to combine different image cues. Okay, so here are some results. This is a comparison of multiple methods on the texture database that we have collected at UIUC. You see some sample images on top. So the database tries to exercise as much variability as possible. So we have very non-homogeneous classes like the marble on the left. We have a lot of geometric transformation, perspective distortion, etc. Some of the classes are non-rigid, or this third one is actually water. So I've tried to be very sort of diverse in collecting this database. And the results, you can see the best performance is achieved by the method of Zhang and Marszalek, which is a bag of features representation with an SVM classifier. Slightly below is my bag of features representation without an SVM classifier, just using nearest neighbors. So you can see that in this case, using an SVM does help to raise performance. And the other three approaches are sort of more traditional texture recognition algorithms. These two, Heyman and Varma and Zisserman, they use fixed size patches as features computed at every pixel location. So this is unlike our framework, which only uses key point locations. And this framework is not intrinsically invariant to geometric changes, whereas we try to factor the geometric changes right into the representation. Yes?
So a couple slides before, you had a pyramid structure that was multi-resolution, but in this case, you don't use...
No, I will talk about it later.
Okay.
In this case, this is just the basic bag of key points.
And when you detect a feature and it has a particular scale, and orientation, and elongation, do you adjust the descriptor based on that?
Right. As I was showing before, we do this normalization. So we discard this information. So we normalize for the geometric changes.
So you take the local image patch and rescale it, or you just...
Yeah, apply basically sort of rotation and non-isotropic rescaling to transform the ellipse into a circle.
Oh, okay, that's what that...
Yeah, so literally the patches we detect are ellipses, and we basically literally transform them into circles.
So
Yes.
there's still an orientation.
Right. Yeah, so that's sort of an annoying fact that's in there, and there are two ways to deal with it. One is to compute rotation invariant descriptors, in which case you don't care what the orientation is. And the other strategy is just use David Lowe's method to find the dominant gradient orientation. And I think we have used both. So the descriptors I use are two kinds of rotation invariant descriptors and also the standard SIP descriptor.
For the different textures, I'd imagine you do quite well in the cloth and the bricks or that sort of thing. Are there certain classes of textures that the feature-based methods don't work that well?
Yeah, so that will actually be my next slide.
Oh, okay.
So let me just finish up with this one. And so the most interesting thing to notice about this is that the performance of our two methods that use these locally invariant features really goes up very steeply with the number of training images. Is there any water?
I'll get you some water.
Sorry. Sorry about this. I just had a cold. So by building the invariants into the features themselves, we don't need as many exemplars as these methods that don't have invariant features, so they need to see the various kinds of transformations represented in the training set. Okay. Okay, so this is an example of a database where a method fails miserably. Thanks. Okay, it's a lot better. So this is a fairly well-known database, the Columbia Utrecht Reflectance and Texture Database. And it mostly consists of very high-frequency textures that look sort of like white noise in some cases. And lighting variations are a big component of this database. So they actually systematically varied lighting directions and camera viewpoint angles to acquire these images. And lighting variation is something that our method does not compensate for. So as you can see, especially the basic method that uses nearest neighbors does not do well at all. With the addition of the SVM, the performance goes up quite a lot though. So you can see that even though our method is not designed to deal with things like lighting changes, with the addition of a discriminative classifier, we can recover from that. But to answer your question, these are the kinds of images that our framework is really not that well suited for. And you can see it on the table here. So our framework works quite well on higher resolution images because the kinds of feature detectors I have shown, they really need to process the image at multiple scales, etc. So if the image is only 200 by 200 pixels, there's not much to work with. In addition, they're good for non-homogeneous textures and the textures that are fairly low frequency, where there are some interesting features or key points to latch onto. If the texture basically looks like some kind of a noise pattern, there aren't very distinctive key points. And finally, as I mentioned, we don't do anything explicit to represent the changes in appearance that result from change in lighting direction.
So do you think the problem then is mainly in the descriptor, not in the actor then? Are you using some sort of SIPT descriptor?
Well, for instance, actually the descriptor is just fine. What you can do with these images is you can compute SIP descriptors on a fixed grid, or even basically for every pixel location, and I think that would work better. Mm-hmm. So I think the detector here is the problem, that there aren't a lot of salient key point locations to detect in these images. Plus, in order to handle lighting variations in a really principled way, you need to actually have some model of the microstructure, the sort of microscopic bumps on the surface. Okay, but now let's move on to object recognition, which is much more interesting. So when we originally designed this method, we didn't really think of it at all as being suitable for object recognition tasks because it has some rather obvious drawbacks. For example, there are no spatial relations, no separation between foreground and background, and no localization capability. So for classification, we can use it just fine. It can tell us that the image contains, say, a bike or a person in it somewhere, but we have no clue where. Nevertheless, originally my intuition was that these representations would fail even at this task, and this is where my intuition turned out to be wrong. So this was rather surprising and served as a source for some insights. So you can see here, just to back up my claim, here's a comparison of two bag of features methods, our method and this other method from Xerox in Europe. They're both orderless methods, and they both outperform Rob Fergus's constellation model. So we want to understand why. Here's a model that tries to sort of do things right, tries to find stable object features, tries to build a part-based representation, and yet we take some sledgehammer and it works much better. So we should try to get a more detailed understanding of why that is. But first I will show results that are slightly more convincing because the Caltech database, there has been a lot of work on it recently, and very many methods get good performance. So a more challenging data set comes from the Pascal network that recently held this object recognition competition, and this is what their data set looks like. It has 4 classes: motorbikes, people, and I think regular bikes and something else, and cars. And test set 1 is slightly easier. It has objects that are fairly well visible in the image. And test set 2 was, I think, found on Google, and it has much more unconstrained statistics, and it can even have several objects in the same image. So an image can have both a car, a person, and a bike. And we want to detect all of them. So here are the results. So you can see that our results are right up there with some of the best performing methods on both data sets. And the results for test set 2 are actually much lower because it's a more difficult data set. So here our results are better than this winner of the Pascal competition. I think these results were actually obtained after the fact. And the results for test set 1 are very comparable to the best results. Okay, but one thing we really want to find out is what does this method do with the object backgrounds? Does it derive additional clues from background correlations, for example? And also, how do background statistics affect recognition performance in general? So to study this, we had the following protocol. The Pascal images, they all come with bounding boxes for the object. So we use these bounding boxes to separate foreground from background features in each image. And then we introduce 2 additional background sets. The first one, this random set, was formed basically by randomly shuffling the backgrounds among all images. So a car image can get assigned a background from a person image or something else. And the second background is basically some sort of a monotonous natural scene of which a few images were acquired over time. So there is some variation, like natural lighting variation, cloud movement, tree movement, possibly cars in the parking lot, etc. So first of all, just to see what happens when we remove the foreground and leave just the background, you can see that the constant and the random backgrounds, obviously they have chance performance by construction, and the original backgrounds are, in fact, the performance is not chance at all, especially for test set 1. So we do get some sort of hints about the object just by looking at its background. And this confirms that there are significant background correlations present even in the more difficult data sets that people have acquired. But the next question is, does the background actually improve recognition performance? So these are results, ROC curves, obtained by training and testing on different feature sets. So FF is just the foreground. So we remove the backgrounds completely and train and test on only the foreground. Then AF const is we keep the original foreground and add the constant natural scene background. AF is the original images, and AF rand is the original foreground plus the randomized background. So you can see basically that the simpler the background statistics, the higher the performance. In particular, training and testing with just the foreground seems to be the easiest recognition task. And if you believed that background would provide additional hints for recognition and improve performance, these tests sort of falsify that hypothesis, at least for our method. There may be other ways to exploit background to improve performance, but not in this bag of key points framework.
This is segmentation, right?
Right, so we used the segmentation just to create these different background sets.
But if you didn't have that hypothesis, then you may reach a completely different conclusion. Like, for instance, if you don't know how to segment the foreground from the background, then the background could be a great clue, not knowing.
Right, but here we don't, so we use the segmentation to combine the features in various ways, but we don't, after we combine them, the algorithm doesn't know which ones came from the foreground and which ones came from the background. So we just take the foreground features from one bag, the background features from another bag, and toss them all together. We don't maintain the information about the separation. So this is just to create various kinds of synthetic data to see what happens when the backgrounds have certain statistics. Okay, so the next question is about generalization. So what happens when the test background statistics differ from the training background statistics? And as you can see from these results, the classifier trained on original images generalizes well to test images with easier backgrounds, but not to the test images with the harder background. And this may be somewhat surprising because you would think that a classifier trained on a certain kind of images would work the best on those exact same types of images. But it seems that removing clutter from the test data set actually improves its performance. So just to verify this hypothesis further, that a generalization is indeed good to easier backgrounds, we sort of reversed the setup and trained on different backgrounds and tested on the original images. So once again, you can see that classifiers trained on the easier backgrounds don't generalize well to these original backgrounds, whereas the two classifiers trained on the same types of backgrounds and on the random backgrounds generalize about the same. So this is interesting, that this classifier trained on completely randomized backgrounds that don't provide any information about the object generalizes well to the original object backgrounds. So basically, to summarize, that background features definitely are correlated with the foreground, but at least for our method, using the backgrounds does not improve the results. And the other lesson is that if we don't know the statistics of the test set in advance, it would pay to choose the hardest training set possible. So training on uncluttered images probably will result in a classifier that will fail miserably on a harder data set. Okay, so next I will take this issue of background statistics and try to exploit it further. How can we get better performance out of an algorithm basically that exploits both the foreground and the background together? And this is the pyramid representation that I mentioned in the beginning of my talk. And it was inspired by sort of two strands of work. The first one is what I call a subdivide and disorder strategy that has been practiced numerous times over the past maybe 15 years. And the strategy consists essentially of taking an image or an image patch and subdividing it into a fixed number of blocks and computing histograms of some features or histogram statistics such as means over these regions. And two examples are David Lowe's SIFT descriptor, which computes in this pattern of blocks edge orientations, histograms of edge orientations. Another example is Antonio Torralba's GIST representation for the image as a whole, where they use steerable pyramid filters and compute averages outputs of the steerable pyramid filters inside this pattern of subregions. And the second piece of work was recently introduced at ICCV 05. It's the pyramid match kernels by Grauman and Darrell. Essentially, Grauman and Darrell, they propose to match two distributions of features in some high-dimensional space by placing this sort of sequence of grids over the space and counting the number of matches that are found in each cell of the grid. So what I decided to do is to apply this pyramid matching not in the high-dimensional feature space, but just in the two-dimensional image space. And what we do in the feature space is standard quantization. So we just quantize the descriptors and find the visual vocabulary. After that, we have some discrete feature types. In this picture here, we have 3 types represented by crosses, diamonds, and circles. And we just deal with each type separately. Essentially at each level of the pyramid, we just compute the counts of the features in each cell separately for each feature channel. And we do this for several levels of subdivision. And at the end, we put some weights on the histograms. Features at higher levels get higher weights, sort of to represent the idea that if we found 2 matches in a really small cell of the grid, that they really are close. So we want to weight close matches higher. And at the end, we concatenate this whole representation and use it inside of histogram intersection kernel.
And this is meant to be the whole image?
Yes, the whole image. So this is sort of a very simple framework. And let's see how it does. So the first data set is a scene category data set. It's a mix of images from several sources. 9 of the categories were obtained from Oliva and Teralba, and 5 others come from Fei Li, and 2 store and industrial were acquired by myself from Google. So this has 15 categories, and it's probably the most diverse category data set that people have used to date. One caveat, though, is that these images are fairly low resolution, about 200 by 300 or so. So here are our results. They're broken down by the number of levels in the pyramid, and also I evaluate performance by using just a single level of subdivision versus all levels together. So you can see, first of all, that using all levels together does result in a statistically significant improvement. And this shows results for 2 types of features. Weak features are just edge orientations. So 16 is the dimensionality of this feature space. We get that from 8 edge orientations and 2 scales. This is designed basically to give an image representation which is very similar to a global SIF descriptor of the image. And the strong features are basically local descriptors computed on a fixed grid. So incidentally, I use SIF descriptors, so this whole scheme has kind of a self-similar structure, that first I compute SIF descriptors, and then I put the text and labels of the SIF descriptors into a larger SIF descriptor, if you will. But the strong features, obviously, we use a visual vocabulary of 200 words. So it's a more discriminative representation, as one would expect, and it does much better. And what's interesting that the performance of individual levels actually drops as we use a lot of subdivision. So if we subdivide the image into an 8 by 8 pattern, our performance actually begins to drop because it already does not have enough invariance. There are too few matches in these small cells of the pyramid. However, if we put all the levels together, the performance drop of the last level gets more or less discounted. So using the lower levels results in more or less the same performance, even with this extraneous level that does not give you enough useful information.
Can you describe the strong feature methodology again in more detail?
Yeah, so the feature extraction scheme is I take fixed size patches on a fixed grid, so something like an 8 by 8 grid and 16 by 16 patches, and compute SIF descriptors of these patches. Then I quantize the SIF descriptors and assign to each its cluster label.
Okay.
So this is with 200 labels.
This is 200 labels. That's not the dimensionality of the SIF descriptor. That's the number of quantized labels.
Right, exactly.
So what are the trade-offs in doing the patch-based thing? Because I think, Triggs and Jury, or I don't know if other people have suggested it, but some people say, well, let's just not even try to find interest points.
Yeah. So in this case, I did not try to find interest points for 2 reasons. First of all, the images, as I mentioned, are fairly low resolution. So from our previous experience, interest point detectors will not work that well. And secondly, for scene recognition, you really need to retain some information about areas of uniform texture, like sky, for example. With interest point detectors, you just lose that. And also, Fei Li has performed some experiments for her, I think, CVPR-05 paper, where she basically showed that interest points have slightly lower performance in a fixed grid. And I more or less took this feature extraction framework from her paper. So I also show her results, which were obtained for 13 out of the 15 categories, but actually the 2 categories I introduced are slightly harder. So if you remove them, our performance would go up slightly. And you can see that this pyramid method really does perform better. So our level 0 performance, which is just a bag of features, is 72%, which is already higher. But by using the pyramid, we go up to 81. So there is a significant difference from previous methods.
Has anyone studied doing feature detection plus regular gridding to see if that hybrid has any advantages?
So this is Fei's work is one I mentioned. And I think you mentioned Jury and Triggs. I don't remember if it was them who did something like that. But I think some of this work, let's see, where was it? Like one of these two, I believe, used the regular grid. So I think this is beginning to be the next area of exploration, trying to go back from interest points to regular grids and seeing, what really works better.
If anyone at this point, since there are two techniques, that tried the hybrid and see if there were some advantages, because you could make an argument that when you get an interest point that is unique and it fires, it's very discriminative.
Right.
But because of these lack of as soon as you get into something that's very texture-like and the performance, the repeatability, when the repeatability goes down, you may as well put something in there, otherwise you're just
right, exactly.
evidence, right? So
yeah.
It seems like maybe a hybrid where you combine both might work.
Right. So I think one of these papers, not sure which one, might actually be a hybrid. I haven't looked at them this closely, but I think it is beginning to be explored. Okay. And this is a confusion table. And the sources of confusion are basically what you would expect. There's some confusion between the indoor categories and some confusion between some of the outdoor categories, like coast and open country. Here's one interesting thing that I can do with this kernel is I can just take a query image and rank all the other images in the database by their similarity according to this pyramid match kernel. So here are some examples of retrieval. For example, on top there's a kitchen image and it's matched mostly to living room images, but I think that at this resolution a human would have trouble figuring out that that's a kitchen. One interesting thing is that this kitchen image has basically the lighting comes from the windows outside and the room is very dark, and some of the retrieved images feature the same lighting scheme. So this matching framework picks up on features like that. Another interesting example is the second kitchen, which has white cabinet doors with dark edges, and what gets retrieved are two images of the same cabinets. This office image with some documents on the wall that also have dark edges. So in this case we have also window frames that look kind of the same. So there is some interesting perceptual structure there. And you can see that in other examples we pick up sort of the global pattern of edges and blobs and the overall spatial organization of the image, including perspective and things like that. Okay, so the next set of results is on the Caltech 101 database. This is an image that sort of illustrates the essence of the database. It's due to Antonio Torralba. He took the examples from each category and averaged them. So I think a bunch of these categories can easily be recognized from the average images, like Garfield and menorah and metronome, stop sign, faces, etc. So obviously this database has very stable global statistics, and that makes it a good candidate for our method, because that's what our method exploits. So here are the results. So what's interesting is that with the weak features at level 0, just a bag of features, we get 15%, which is consistent with the most naive baseline tried on the Caltech database, something like global image correlation. But as we use the pyramid, after 3 levels, we get up to 54%, which already beats all the other results that have been published to date. And with the strong features, we get even better performance. We go from 54% to 64%. So as far as these comparisons go, one thing to note is that people have measured results in different ways. In some publications, the result is reported as the total percentage of test images classified correctly, but that turns out to be biased. Because some of the easier categories actually have the most images. So the recommended way to compute the performance is to actually average the recognition rates of the individual classes. And in this case, Alex Berg reported his results with 15 training images per class. And if we use 15 training images, we get a rate of 56%, which is significantly higher than his. So this is interesting. I think the reason our method shows such an improvement is that nobody to date has really tried a global method like this on the Caltech database. The existing methods are either bags of key points, features of various kinds that are completely orderless, or geometric matching or correspondence framework also on top of sparse features. So nobody has really thought to exploit sort of global geometric information of a more or less dense feature grid. And here's some more detail about our performance. So some of the classes we do well on, they either have funny artifacts. Actually, a few classes on the database have these rotation artifacts that make it easy to recognize them. And other images that are either uncluttered or sort of are interesting natural scenes that have some texture to them, like this Joshua tree or the okapi that has some stripes. The things that are hard to recognize are textureless animals, very thin objects like ants, or objects that camouflage really well in their environment. And I think this is more or less the general picture for a lot of these methods that have been tried on the Caltech 101. And also here are the top 5 confusions for our method. So just as a sanity check, it's comforting to see that they're between very closely related objects. And some, like David Forsyth, would say that there's even no point in making a distinction between a ketch and the schooner. Unless you're an expert on ships, they just look the same to you. So there's no point in making them 2 separate classes. So finally, we've tried our method on 2 data sets that were friendly to it because they had some stable global structure. So then we decided, well, let's take a data set that seems ill-suited because it features a lot of clutter and a lot of geometric variability. So this Graz data set for people and bikes, as you can see from the examples, there's quite a bit of scale variation. So you can have a very small bike somewhere in the image. Or for people, you can have people, either some pedestrians in the distance or some close-ups. In some cases, I think you can even have an image of a hand in a database, and that is labeled as a person. So there's a lot of variability that our method is not really designed to deal with. So here is a comparison. So just at level 0, using these non-invariant features, we get performance which is lower than the performance of 2 geometrically invariant bag of features method. But when we use the pyramid with 2 levels, our results become comparable, at least to these Opelt and other results, not to the Zhang.
So the distinction between L0 and Zhang is that Zhang centered the descriptions on interest points.
Right, right.
And you gridded yours.
Right. Plus, there was also the use of multiple types of detectors and descriptors, as I mentioned in the beginning, etc. So it's a really sort of optimized bag of features method, very carefully engineered.
Now, why did you, for your strong descriptor, why did you stop with SIFT and 200 labels? I mean, what happens if you increase the number of quantizations?
Okay, so that's an interesting question. I actually have some results for, say, 400, and I excluded them because they're identical to 200. It was a little bit surprising because with a standard bag of features, if you increase your vocabulary size, usually the performance goes up. But for us, you see the performance increase at the first level, but as you add the several levels, you know, the performance becomes essentially identical.
Have you tried, a lot of times you do that sort of bag of features, where there's maybe 10 features that fire all the time. Have you tried getting rid of those, like the top 10, and just matching ones that are more discriminative, or?
No, we didn't do anything like that. No feature selection of any kind. Okay, so what's interesting about this is that it seems that global spatial relations do help even in data sets that have a lot of geometric variability. So it really makes sense for that reason to exploit context in object recognition systems. So this is very recent work. It was actually submitted to CVPR. And I'm planning several extensions to it. One is to try try this kernel for clustering. For instance, it could be quite suitable for spectral clustering or things like that. So to do some unsupervised discovery of object categories. At the NIPS workshop on object recognition, Kristen Grauman actually showed some results for clustering, and they were quite interesting. So since my method outperforms hers, it would be also interesting for me to go in this direction and see what happens. And another thing is sort of segueing into my next topic, which is part-based models for object recognition. As I said, I want to find ways to integrate context into that. And there has been some work from Kevin Murphy and Antonio Torralba and others showing that context really does help a lot. OK, so the last part of my talk, I'll go through it quickly, is structured part-based object representations. So as I mentioned in the beginning, the real way that a lot of people in the object recognition field want to recognize objects is by finding some meaningful and geometrically stable parts. So if we have images of cars, we want some configurations of key points that will really reoccur repeatably. So for instance, you can see some examples here. There can be this configuration around the back wheel that recurs, or the front of the car, despite variability such as cars having different colors, or maybe even just the wheel. So we can take a back wheel from one car and match it to a front wheel of another car because the two wheels, locally, they look the same. Or if we have an SUV and a regular car, maybe we can match the middle. So what we want is a vocabulary of these kind of parts to represent objects. So the ideal way to acquire this sort of vocabulary would be a direct search for geometric correspondence. So if we have a bunch of images of ducks, we would like to perform a simultaneous search and find some local patches that look the same in all the ducks. Like this head, it happens in all images of Mandarin ducks, so we would pick it out and say that that's a good duck part. The only problem with this is that computationally, this sort of strategy is actually infeasible. We can't perform a simultaneous multi-way correspondence search. So a more practical approach would be to reduce it to pairwise matching, which can be done reasonably. So we take some random pair of training images and perform matching between them, and find some part that occurs in both images. And we call it a candidate part because we must also determine whether this part is stable and repeatable in the rest of the data set. So once again, we take the candidate part and perform pairwise matching with each validation image to make sure that it reoccurs. And we use the repeatability of the parts in the validation images to rank them. So once we evaluate a lot of candidate parts, we pick out a fixed number of top scoring ones and call it our part dictionary. Following this, we can learn a discriminative model of the part statistics for each category. So what I have actually used is a discriminative maximum entropy model, but another classifier would do just as well, such as an SVM. And the features for this classifier would be basically the repeatability of each part from the vocabulary and each image. So since these parts, as you recall from the previous slide, are composite, each of them can have multiple regions, the detections usually are partial. So if a part has 100 regions, maybe we only found 50 of them. And then our repeatability is 0.5 for that part. So we take all the repeatabilities, combine them into a feature vector, and use it in a discriminative framework. So here are some results for the Caltech data set. And the top two rows are the top parts that were found for each class, such as planes, cars, faces, and motorbikes. And you can see that for cars, actually, the parts have a lot of clutter. This is because the car rear images have very monotonous backgrounds. They were all acquired basically with a camera in the front of the car, always sort of at a fixed height from the ground, etc. So the road the horizon is always, the position is the same. There are the same kinds of features on the side of the road, like trees and buildings, so a lot of that gets picked up.
What is the basic feature detector used to?
Oh, so here actually the feature detector is different from the ones mentioned earlier. It's a detector that comes from Jury and Schmid. So it finds more or less circles in an image. You can think of it as a half transform looking for approximately circular configurations of edges. And it disregards internal structure. So if it finds some curve, it draws a circle around it. And there can be interesting stuff going on inside the circle.
Why did you decide to use this one for this work?
Yeah, so this detector, so obviously I started by experimenting with the previous ones, but they really don't have the repeatability that one would want for these kinds of categories. And I really, for this work, rely on a lot of repeatability because I perform geometric matches. It's not as important for bags of key points because you disregard all spatial information. But here, geometric stability and repeatability is important. So the Laplacian, for instance, it just looks for uniform blobs. So it wouldn't really find things like the eye because there's some interesting stuff going on and so on. Or even a wheel, because wheels usually aren't uniform. They have also some structure inside. So this turned out to work much better. But so far, this is also work in progress, and I don't have sort of comprehensive comparison results for all the different kinds of detectors. In the third row are histograms of part repeatabilities for positive and negative images. So for really good parts, we would expect the repeatability in the positive images, which is this red curve, to be significantly higher than for the negative images. So you can see for the faces, it's very good, and for the motorbikes, it's not very good for the planes. So the plane parts are really not that good at distinguishing between positive and negative instances. And you can also see this in the plot of validation scores for all selected parts. So our validation score is actually the chi-squared histogram distance between the positive and the negative histograms. So the airplane parts are the weakest because, once again, airplanes are sort of thin objects that don't have repeatable texture inside of them. So that's not very good for our detector. And you can see that the recognition rate on top for the airplanes is not the best. Okay, so here are some examples of successful detection. So in the middle are bounding boxes of the different parts that were detected in the test image. And over here are the actual interest regions that were assigned to the object. So you can see that this approach can deal with things like funny facial expressions or clutter, somebody is sitting on top of the motorbike, etc. Here are some failures. So as I mentioned, airplanes don't work that well for localization, and you can see that what's localized is some kind of clutter instead of the airplane. Also, this method is sensitive to lighting because of the nature of the Caltech face set. Most of the images were acquired basically indoors with a flash, and there are relatively few examples like this, so they didn't make it into the training set. That's why when you get an example like that, you don't detect anything. And for the motorbike, this is the only image, I think, that was misclassified. And what goes wrong here is the contrast is very low, and you can't see the front wheel properly. It so happens that in our model, the front wheel is actually the strongest feature. So here are also some results on a slightly more difficult database that I have acquired. It has 6 bird classes. You can see that the quality of the parts sort of varies widely. The weakest parts are for egrets, which are thin textureless objects, once again. But what's interesting is that in this discriminative framework, weak parts do not necessarily translate into the weakest performance. It depends on the kinds of confusions you can get between these classes. So it's possible that if you have a class with very weak parts, it actually becomes the main confusion class. So everything that the classifier is not certain about, it will assign to this class. So it can even, with a sufficiently weak classifier, become the class with the highest performance, because everything gets assigned to it by default. So one has to be careful when doing these kinds of things. Here are some successful detection examples. For instance, these two ducks, the male and the female Mandarin duck, don't get confused because we trained the approach only on these kinds of ducks. And for owls, some of the interesting features that get picked up are the eyes. And here are some failures. So what went wrong in the middle case is that the duck's head is facing down, and in this particular implementation, we did not actually account for rotation, even though it would be easy to do so in principle. So this can be very easily eliminated. Okay, so this concludes my talk, and some of the future research directions is to complete the evaluations for this method, perform some baseline comparisons with the bag of features methods I've described earlier. I have some anecdotal evidence from Zhang and Marszalek that their method currently performs worse than my part-based method on the BERT database, but they actually need to run the experiments with exactly the same kinds of features to get comparable results. Also, so far, I've only evaluated this part-based model on whole image classification, whereas it's, as I showed in the examples, it's in principle capable of localizing the objects. So the next step is to evaluate this localization quantitatively. And also to incorporate some relations, because currently this model is essentially a bag of parts. There is no information about how the different parts relate to one another, and this is something we want to fix. And finally, ultimately, we want to handle a much wider range of objects for which texture is not the key feature that you want to use. For instance, with these cows, if you start learning models based on the patterns of spots or the color, you will be completely lost. So we need something more shape-based, especially for textureless objects and even more difficult objects that are, say, transparent. So that's all. And there's more information on our group webpage. There are some data sets. The texture data set and the BERT data set, for instance, are available currently. Also some presentations on dollar publications.
Thank you.
Some questions?
Mm-hmm.
Can you comment on your timing performance of techniques that you talked about?
Okay, so they sort of run the gamut. The part-based model currently is very slow because it does geometric search, and the geometric search is extremely time-consuming. So to get the results, for instance, on the Caltech 101, it would take something like, a week with everything, training, testing, feature extraction. But the spatial pyramid method, on the other hand, is very fast. The subdivision that I've described, it basically can be carried out very quickly. And the kernel, the histogram intersection kernel, also can be evaluated very efficiently, so that takes something like minutes. And the other bag of key points methods where you use geometrically invariant features, the feature extraction stage, they're somewhat time-consuming when you have to find, the characteristic scale and the shape of the key points. But classification is relatively fast because SVMs are used. So it really varies and can also be, improved a lot by more efficient implementations. Mm-hmm.
For methods, how for scaling to a lot of different objects, say beyond the 4 test cases, that sort of thing, which methods? I mean, the geometric method seems to be the best for that because you have a little extra information, where you have the geometric information. How do you do you see these methods scaling to, say 100 objects?
So some of them, the pyramid approach I've tried on Caltech 101, so that already works on 100 objects. The part-based approach, the complexity is linear in the number of classes, so basically it's just a matter of computation time, so some optimization would be required. just to do it using the method I have right now. But there are smarter ways you can go about it. For instance, one idea that seems very attractive is part sharing. Have sort of a global part dictionary that grows maybe logarithmically instead of linearly with the number of classes. And I think this is something that you would need ultimately to deal with a lot of classes, but I don't have any ideas yet how to sort of change my part-based framework to do it.
When you were introducing the 3 problems, and you had object recognition in the middle, those pictures you showed on the first slide had little boxes around the objects.
Right, so that's from the Pascal dataset. So the boxes are available, but they're not used during training. So actually, all of the approaches I've described are semi-supervised or weakly supervised. So they don't use the bounding boxes for training.
And is that what everyone does, or that's just
No. I think right now there's sort of a preference for weakly supervised methods because they don't require so much annotation. But a lot of the part-based methods currently in existence need strong supervision, so they actually need the bounding boxes or even need the individual parts to be marked up. So sort of there's a variety of approaches out there right now. I think it would, the consensus is it's important to move to weakly supervised setting. But there are some problems there with evaluation. For example, if you don't have ground truth, how do you evaluate localization and so on?
So have you done any localization in your work?
Not yet. So that's my future work. And for that, I'm afraid I will just have to go by hand and, find out lines of all the birds. It's still realistic for my size of data sets.
Right.
But we have to start thinking about how we can evaluate these things without having to provide the ground truth. Maybe there are some proxy tasks or some smart ways of doing it.
Right. Aren't there cooperative labeling websites where you do that kind of thing?
So right now there are some things that were introduced where people can label images, like Label Me from MIT. So it may be that it's right now there is not a lot of pressure to move to weak supervision, because if you can have these approaches where people will actually be willing to annotate and provide quality annotations for large databases, we can use that information well, if it's available. So it's not clear yet. I mean, in principle, it's very expensive to provide manual annotations for large data sets. But, for particular tasks, people may be willing to do it.
Right. I don't know how expensive the economics are, right? If you do some of the labeling abroad or things like that.
Right.
There's a certain cost just for acquiring the images in the first place. So.
Right. So it all depends basically on your application. So Pietro Perona has calculated a figure, I think, 1 billion to annotate a database of something like 10,000 classes, and I don't remember, several thousand examples for each class. He had that derivation at the NIPS workshop.
But that database doesn't even exist yet.
Right.
Because someone has to first name
That's
each
true.
image, right?
Yeah, so it's a little bit abstract at this stage.
Any other questions? Okay, thanks again.